All right, let's go ahead and get started. I do want to welcome you to the second part of this worksheet. This is calorimetry problems. We're going to start with number 7, but you are going to need a calculator for this one, so if you don't have one handy, go ahead and pause the video and get back to us. Here we go. Number 7 says this. When a 12.8 gram sample of potassium chloride dissolves in 75 grams of water in a calorimeter, the temperature drops from 31 degrees to 21.6 degrees Celsius. We want to calculate the delta H for this process. So let's take a look at kind of what the scheme is. So we've got this dissociation happening, right? This dissolving happening. It's happening in a reaction vessel. I've kind of sketched it off here to the right. So the reaction vessel is in the center here, and I've drawn with like little green dots the surrounding water, right? So these are water molecules all around. Now, this is an endothermic reaction. I can tell that because of the fact that the surrounding water, when I look at the temperature change, we're going from 31 to 21.6 degrees Celsius. That tells me that energy is flowing from the water into the reaction vessel, right? It tells me that the direction of energy flow is this way. The water surrounding the reaction is getting colder from 31 to 21.6 degrees Celsius. That means the reaction is requiring energy to proceed. We call that an endothermic reaction. Endothermic because it requires energy. Now, how much does it require? Well, that's what we're going to find out. Here's how we're going to do that. Well, the heat lost by the water, because of the first law of thermodynamics, must be gained by the reaction. They can't escape anywhere. It can't go anywhere other than into that reaction. So if we can determine the amount of heat lost by the water, we're going to know the delta H, right? Now, we also know, by the way, that the delta H is going to be positive. So I'm just going to go ahead and put a plus sign right there because endothermic means that the delta H is positive. So whatever I get, I'm going to put a positive sign in front of it. So let's determine the heat lost by the water. We've got 75 grams of water. We know the specific heat is 4.184 joules per gram per degree Celsius. And if we don't know it, I'll give it to you on the quiz or exam, so don't worry about it. And then we want to determine the temperature change. Now, I'm going to tell you that technically, I should have put the 21.6 heat to the left minus 31.0 since it's TF minus TI. But the way I've worded this, I've said heat lost by the water, right? So with words, I've made this positive, right? I've made it positive by saying this is how much I've lost, right? It's like saying the wave pushed me back 3 feet, right? I don't have to say it pushed me negative 3 feet. It just pushed me back, right? And it pushed me back by this magnitude, 3 feet. In this case, I'm just getting a positive number to make things easier on myself and then using the words to allow me to get that positive number. So that's equal to delta H. So let's do a quick calculation. When we say 75 times 4.184 times 31.0 minus 21.6, I get this big number, 2,949.72 joules. Let's shave some significant digits off of there. We want only 3, so we'll make it 2.95. We'll also convert it to kilojoules, and so that is the delta H, right? That's the delta H. So I'm going to say that the delta H is positive 2.95 kilojoules. That means it requires that much heat to make this reaction go. So heat plus the potassium chloride will dissociate into potassium ions and chloride ions, and we're done then with number 7. Let's go to the next one, number 8. Number 8 says this. It says a 250 gram sample of zinc is heated and then placed in a calorimeter containing 65 grams of water. The temperature of the water increases from 20 to 25 degrees Celsius, right? So that gives us a hint of the direction of the heat flow, right? The water is going from 20 to 22.5 degrees Celsius. Now, there's no chemical reaction involved here. I'm just placing a heated piece of metal into some water and looking to see what happens. The specific heat of zinc is 0.390 joules per gram per degree Celsius, and they want to know what's the initial temperature of the zinc metal sample. And they're telling me also that the final temperature of the zinc and the water are the same, so they're in equilibrium. So here's the strategy that I'm going to use. I'm going to say the heat lost by the metal is equal to the heat gained by the water. right? Now, little note about signs here. This is important. Notice how, well, let me do this. I'm going to say the heat lost by the metal is the mass of the metal, which is 2.5 grams, times the specific heat of the metal, which is given to me as 0.390 joules per gram per degree Celsius, times the change in temperature. Now, I got to be careful here because of the fact that if I'm going to be consistent, I'm going to want delta T to be final temperature minus initial temperature. I'm looking for the initial temperature. That's what they're asking me for in the problem. Well, the final temperature of the metal was the equilibrium temperature. It was at 22.5. So that's the final temperature. So I have to say 22.50 minus the initial temperature, right? Now, I know that the initial temperature is going to be higher than the equilibrium or the final temperature. That means this part is going to be a negative number. So to counteract that, I'm going to have to put a negative sign in front of all of that, right? So heat lost means that the amount of heat is lost. I put a negative in front of that. That allows me to kind of be able to cancel out units properly and have the right sign at the end. Is equal to, now this side's going to be easier. The heat gained by the water, it's 65 grams of water. Specific heat of water, 4.184 joules per gram per degree Celsius. And here's what happened to the temperature. The final temperature, again, was 22.50, but the initial temperature was 20 degrees. When I subtract those, I'm going to get a positive number. So now what I'm going to do is just do a little bit of algebra, simple algebra, in fact. I'm going to say this. When I multiply this times this, I get 0.975. Keep the negative sign right there. That times 22.50 minus T initial in parentheses is equal to, all this across is 679.9. Then I get 22.50 minus T initial is equal to, I'll do that division and I get minus 697.3. Notice that minus TI is equal to minus 697.3 minus 22.50. So minus TI, that's initial temperature of the metal, is equal to minus 719.8. And I'll multiply both sides by -1 and get that the initial temperature of the metal was 719.8, and that is degrees Celsius, and that'll do it for that problem. Let's move on to the next one. Number 9 says this: a 13.5 gram sample of gold is heated in a calorimeter, and then placed in a calorimeter containing 60 grams of water. The temperature of the water increased from 19 to 20 degrees Celsius, right? So that means we put a hot piece of metal into water, it heated up. That makes sense. The specific heat of the gold is 0.130 joules per gram per degree Celsius. They want to know what was the initial temperature of the gold. Here's my strategy. The heat lost by the gold is equal to the heat gained by the water. Again, put a negative in front of there because this right here is going to turn out to be negative. So a negative times a negative is a positive. The gold was 13.5 grams. Its specific heat, 0.130 joules per gram per degree Celsius. And I'll multiply that by the change in temperature, which is 20 minus Ti, T initial, is equal to 60. That's the mass of the water, times 4.184. That's the specific heat of water. And this is the temperature change, 20 minus 19. That's degrees Celsius. So I'll just do a little bit of algebra now. And we get this. We get minus 1755 times 20.00 minus Ti is equal to 251.04. I'll continue the algebra. I'm going to divide both sides by negative 1755, and I get this number, negative 0.1430. So I'll bring the 20 to the other side as a negative 20, and I finally end up with initial temperature of the metal of 20.143 degrees Celsius, and that'll do it for number 9. Let's go on to number 10. This is the last one. Number 10 says this. It says a 28.4 gram sample of aluminum is heated to 39.4 degrees Celsius and then placed in a calorimeter containing 50 grams of water. The temperature of the water increased from 21 to 23 degrees Celsius. That must mean that the water was cooler than the metal that was dropped into it. What was the specific heat of the aluminum? Same basic idea here. The heat lost by the metal, in this case is the aluminum, is equal to the heat gained by the water, right? We're going to have to put a negative sign again in front of this because of the fact that heat lost means the amount of heat is negative, right? So when you see heat being lost by a particular system, that means you're going to have to put a negative in front of it. The reason is because of the fact that delta T is going to give you a negative number. Notice the final temperature was 23.0, That was the equilibrium temperature. And the initial temperature was 39.4 degrees Celsius. So this number right here, small minus big, is going to give you a negative number. You got to counteract it with a negative right there. So we got negative 28.4 grams times specific heat of the metal times 23.00 minus 39.4. That's equal to the heat gained by 50 grams of water, heat gained by the water, times its specific heat, 4.184 joules per gram per degree Celsius, times the change in temperature. The final temperature, 23.00 degrees. Actually, this should have been 23.00 minus 21.00. I don't think that other zero will make a difference. And that's degrees Celsius. We have 465.76 times the specific heat of the aluminum is equal to 418.4. I'll do the division and I get the specific heat of the aluminum to be 0.898 joules per gram per degree Celsius. That will do it for this worksheet. I'll see you on the next one. Thanks. Bye-bye.